Hello everybody. Thanks to following this presentation. I am Philippe Legoupi, the product manager of the NC software, and I will do the presentation for this webinar. During this webinar, I will introduce the usage of opti-tool and opti-power to avoid breaking tool on the first pivot. After that, I will explain how NCSimul can help you to troubleshoot any program which contain probing sequence. And I will highlight a function of NCSimul is the tool magazine function. You will see what is possible to do with this function. And I will finalize my presentation to review the major function we deliver with the version 2021.1. One, it's about a new feature. It's a singularity point analysis to analyze the 5-axis simultaneous program to analyze singularity point and performance. And the other main improvement we did, it's automatic intermediate stock computation and management during simulation. Normally, OptiTool is used for medium or mass production to optimize the CNC program by reducing the haircut, modify the feed rate to have a constant chip thickness or chip slope. But you can, in combination with opti-power, you can use it on before the first pivot to do a cut analysis, extensive analysis of your cutting condition with opti-tool. You can reduce the haircut, like you see here. You have a cutting motion which cut nothing will be replaced in rapid. You can also recalculate the approach motion and retract motion and with opti-power you are able to limit the power consumption. And at the end, you rewrite a new CNC program and respecting your original syntax. And the benefit of this usage is very simple to use this software. You remove your haircut, you increase the feed rate in tangential motion, and you prevent broken tool with opti-power. And of course, you reduce machining time. Opti-power module is used to calculate the power, the torque, and the cutting force needed to remove material. We can also use opti-power to optimize your program by limiting the power consumption, just to avoid the premature tool break and wear. And the calculation of these three parameters are based on two things. One is the material to cut, and the second is a geometry angle of your tool. For the material, the opti-power database is based on the ISO standard. We call that PMKNSH material, and you have to define the axial angle and the radial angle of your tool in the tool library. Before using opti-power, you need to prepare some things. It's just the tool definition. You have to define what we call axial helix angle and the radial helix angle. And the second thing, before doing the cut analysis, you have a section stock material, and inside you have to select the material type. Is it metallic, aluminum alloy, or something like that? And for each family, you have a designation to select. And it's not mandatory, but if you know the empty power of your machine in kilowatt, you can define it. And this value will be added to the material power consumption. After starting the computation, you can use the graph window and the setting you will see on the right to activate which curve you would like to see. You can also have a complete curve of your program. You can display it tool by tool, and you can zoom like you do on Google Maps. You can zoom with the shifts and Control plus mollet, you can zoom horizontally, vertically on the curve. It's very useful to follow the power consumption, use the graph, and in the info window, you will see the max reached during the analyze.
After using NC-Simul to troubleshoot a new CNC program, further solidify the process by using opti-tool and opti-power to avoid tool breakages during the initial machine prove-out. First, define the cut analysis parameters, then select the tool sequences to include, and finally, define the stock material type and material designation to calculate the power, torque, and axial force of the spindle. After computing, the report window provides information about the cutting conditions and the maximum values found during the analyzation. It also includes data such as the power, torque, cutting force, chip thickness, feet per tooth, and many more. Use the graphing window to observe an overview of the parameters evolution. Displayed here is the power output required during the roughing toolpath. Notice that there are some abnormal spikes. Zooming in on the curve displays the active program line in question. These sudden increases in power can damage the tool and can decrease its lifespan or even break it. To eliminate these spikes, perform a cutting conditions optimization. Select the desired toolpaths and define the strategic parameters. Limit the power consumption to 5 kilowatts for the process. Since NC-Simul will reduce the feed rate during the spikes, it's also advantageous to define a minimum feet per tooth to avoid being under the minimum chip thickness. During this computation, NC-Simul also completes an air cutting optimization, defines the modified approach and retract distances, and selects the new maximum feed rate for any motion outside of the material. Use the optimized graph window to analyze the effect of this optimization. First, look at the new feed rate and notice the many changes that have occurred in the toolpath. Next, look at the power consumption curve. It is now capped at 5 kilowatts. To analyze the feed rate consumption, navigate to the bottom right of the 3D window and the feed rate reduction to 1390 millimeters per minute can be viewed. Selecting the compare mode activates a side-by-side view of the initial and optimized toolpaths. The feed rate for this air cutting motion has been increased to 6,000 from the originally programmed 2,540. Details on cycle time computation for the complete program and for each sequence can be found in the report window. The speed gained outside of material during the air cutting optimization more than compensated for the time lost by safely reducing the power consumption of the machine and ultimately resulted in a slight cycle time reduction. Lastly, generate the new G-code file using the save icon. During this computation, NC-Simul writes the new program, duplicates the current simulation process, decodes the optimized program, compares the trajectories, and launches a new simulation to further verify that the rewritten G-code is correct. A checklist outlining these operations appears after computation, and a text file comparison is launched automatically. Ultimately, by utilizing opti-power and opti-tool, the very first prove-out at the machine can be completed without the risk of tool breakage.
You can use also NC-Simul to troubleshoot all your probing sequence you put in your program. And NC-Simul is able to analyze the behavior of your probing sequence. And NC-Simul support any kind of probing macro coming from Renishaw, Bloom, or Machine Tool Builder, or write by the customer also. We can support any kind of device, probe device, like multi-ball probe, disc probe, cylinder, and also laser for tool measurement. As we support the real macro of your machine, we are able to have the same input checking. That means if you do a mistake, you have the same alarm that you have on your machine. And it's the same for the report. As we support the real macro, you have access to the report variable coming from this macro, and you can use it for test it or write in in a report file like you do on a real machine. And also, function with it very interesting for anti-simul, you are able to enter some deviation during the probing, and after that you can check your escape sequence to be sure there is some time when probing is wrong, you eject the palette, or you modify the tool composition and you redo another pass, and it's why you can predict what's gonna happen on your machine if you have some trouble during the probing. And the benefit of this function is you can use antisimul to, if you have no possibility in your CAM system to generate a probing sequence, you can use a copy and paste and add manually in the program and simulate it after. It can be very useful for you. And we support the complete verification of work offset adjustment, tool measurement, tool compensation adjustment, also macro for tool breakage detection, and sometimes you use a probe to do a stock or feature presence, and so on. All probing sequence are supported by the software. Of course, you can use NCSimul to be sure to verify everything is correct. All parameters are set correctly in your probing sequence. You can also, with deviation input, you can verify your escape sequence. And as you do a simulation, of course, you protect these very expensive tools, which are the probing tool. And as you handle everything before going to the shopper, you are sure you will not have error message alarm on your machine during the first probe. How the probing works into Ultisimul. First, you need to put a special function. It's a probing activation. You need to put it just before the program which contain some code like a G31 or measure for Siemens. You need to put this function just before the program to activate the probing computation. After that, each time NCSimul decode a G31 or measure function, it starts automatically a simulation. It's a black box simulation to have the correct stock shape, and it stops the simulation just before the block to calculate the exact contact point between the ball, the cylinder, with the element contact. Can be the stock, the clamp, or machine axis. And during this process, you will see there is a dual progress bar. The green is during decoding, and here you can see there is a G31 or measure function, and NCSimul start a black box simulation. And when the red progress bar reach the green, NCSimul continue to decode until you find another probing code. And it's possible also to add to stop this behavior if you have a program which contain no probing code, or if you don't want to simulate probing code in this program, you can cancel the probing action of NCSimul. After put a probing activation function before the program, you have to set probing parameter, and these parameters are used during the black box simulation. You can set a specific simulation tolerances for material removal, and you don't need to have a very fine accuracy during this process. The goal is to have the fastest simulation is possible to have, and I encourage you to increase the tolerances to have a fast simulation. And because this, just to explain why I encourage you to have this kind of tolerances, is because NCSimul calculates the contact point in 2 times. First, during the motion of the probe, he finds all facets in contact with the ball, and after that, he uses the vertex of this facet to recalculate the surface. And at the end, he calculates an exact contact point. It's mathematical computation between sphere and surface. This is why you can increase a little bit the tolerances to have, because at the end, the tolerance have no effect on the probing point calculation. And also there is an option I encourage you also to use is to simplify the tool, because more the tool are complex, more the simulation is long, and the goal during this decoding is to have a fastest simulation is possible to have. And another way to speed up the simulation is to simplify the tool shape. And the simplify is to have what we call monotonous tool in Y. That means there is no internal hole inside the tool, and you speed up by 2 sometimes the simulation speed. When the program is completely decoded, you can access to the probing report. To open this report, you can do a double click on this function, or you can use a right click and select probing activation to open this window. In this window, you will find first a list of contact points for each probe. You will see the element in contact, can be a machine axis, can be the part, can be the stock, can be the clamp. You will see also the current machine position for the contact point and the position of your probe code. And you can see in this list, you will see this is the G31 on the line number 9000. And you can see this line was in subprogram called by this subprogram called by this subprogram in this file. And it's possible to enter deviation. You can enter a value when you would like to test what's is going when you enter deviation. Do you have an alarm? Do you jump at the correct line? It's why you can use this parameter to predict what is going to happen on the shop floor when there is a trouble during the probing. And at the end, it's possible to print the report. You have a RTF file you can print. There is some probing option you can use. First one is it's in the machine definition. There is a section probing in the machine, and in this panel you can define which element you would like to ignore during probing. And by default, the element we ignore during probing is the part, because normally the part is in the process just used for comparison at the end of simulation. And when you do inspection at the end of your program, it's better to ignore the part because the stock and the part, the face are very close, and sometimes the probe can touch the part or can touch the rough stock. It's why you can decide which element you would like to ignore during the probing computation, the probing contact point computation. You can also modify dynamically this setting with interactive comment. If in your program you put a comment with a syntax like this, probe underscore inner part on, that means you activate the part ignore. You can put on off, and here you have the list. You can do the same for part, stock, clamp, tool, and machine. And the probing, you need to know that after decoding, NCSimul store all the point in the job, in the process. That means if you reprocess your program, automatically NCSimul reuse the points saved in the project. You don't need to have the black box simulation during decoding. It's the same. It's always to speed up the decoding time. And as we store the contact point and we store each line, if there is a desynchronization, if you add a sequence between your probing, Antisimul will detect it's not the same probing program, and it will automatically restart the simulation. It's possible also to manually force to Antisimul to recompute everything. You have an icon here, the green icon with a little probe. If you push on this button, you ask to Antisimul to recalculate everything, probing, simulation with decoding.
To increase productivity and reliability, CNC programs perform more and more probing operations. The programming of these operations can be a nightmare due to complex cycles with many parameters. NC-Simul allows for the development of the probing toolpath and protects these very expensive tools. It supports any kind of probing macros like Renishaw, Bloom, CNC Builder, Machine Tool Builder, or anything written by the customer. By decoding probing macros with the same exact logic of your machine tool, it is guaranteed to send a safe program out to the shop floor. NC-Simul is very useful to troubleshoot probing operations such as work offset adjustments, part or fixture presence, tool offset adjustments, tool breakage detection, and in-process inspection. NC-Simul can also simulate any type of probing devices like multi-ball probes, cubes, cylinders, discs, and lasers. The probing activation function allows for the calculation of the contact point during program decoding. Opening it gives access to the probing report, where a list of contact points for each probe used in the program can be found. For each contact point, there is information about the element in contact, the program name, position of the machine axes, list of macros called, and 3D and program windows showing the block of each measurement point. Unlike in a simulation where everything is perfect, it's possible to define some deviation to see if the probing reacts correctly. Here, -2 millimeters is entered on the first two contact points to see what happens when the rough stock is smaller. After decoding, the work offset adjustment can be verified. In the status window, the work offset values before and after probing are shown. In the variables window, you can monitor the calculations of the probing macros. In this case, the Renishaw output variables are displayed.
Next topic, the tool magazine. The tool magazine functions contain all the tools needed for simulation for one process. You have one function per simulation process. And how it's work. During decoding, each time you have a TM6 in your program, NC-Simul first look if in the tool magazine the tool exists. If not, he is looking if the tool exists in all the tool library file you link to your project. It's why we can say tool lib file are seen by NC-Simul like a tool database. And it's possible to overload all tool parameter in the tool magazine. That means you can have one tool lib can use by several machines. You can grab a tool from a tool library and change the tool number for this specific project, or you can change some other parameter if you want, but you can overload all tool parameter in the tool magazine. And we store the link of the external file in each project. It's why you can also update on demand. If you do a modification in one tool lib, you reopen the project, you can update your tool. It's on demand. And the benefit of this tool magazine is to store in the project for traceability. You store the tool used for simulation. 6 months after, you can open a project and you can update if you want, but you can see the difference between the before. And also, a tool magazine can contain tool coming from tool library tool file, or you can also use tool coming from tool management system like Antisimultool or Zoller. And you can also update your resources on demand. Tool parameter customization, it's only for the current project. And you can do an assembly. You can do the positioning of your tool. It's very useful to use to put tool on turret and orient the tool assembly correctly on the turret in the tool magazine function. Some explanation about the tool magazine UI. First, you have a group of icon just to export and import toolmag. That means you can prepare a tool list and you can save it in case of a similar part. You can reuse an existing tool list. And it's possible also with the last icon on the right, you can select external tool library file, .tlib file. You can select many if you want and do your market to create your tool list. Second group is it's when NCSimul is connected to a tool management system like a TMS Dollar or NCSimul tool. You can have access to consult your database. You can do some query. You can do some search with query, or if you know the tool ID, you can load directly. Or it's possible also to select tool list in Zoller and NCSimul tool. So you can create some tool lists in this software, and you can grab and directly retrieve all the tool, and at the end you have a function to replace tool, but these functions are used when you use a connection with a system, tool management system. And the last group, it's when you have tool, you can edit all parameters of your tool. You can redefine the composition, you can do the positioning of the tool, and you have two icons to clean, or you can remove all, or you can clean all unused tool. And the last icon, it's when you would like to do a simulation with a smaller tool, when the wear value is defined, you can automatically reduce the cutter size and do a simulation with this tool.
The main difference between a milling and turning simulation creation is at the tooling level. The rest of the actions are very similar, whether it's machine choice, the setup preparation, or any other components. In turning, there are more elements to put in position, such as the tool holder, insert holder, and inserts, and then it is necessary to correctly orient the tool assembly on the turret. The tool magazine function of NCSimul is the place to set up the tooling for the machine. There is one per simulation process located before the program, and it opens with a double click. Display the tools in list view to see the tool number, tool name, station position, and reference. Alternatively, display them in machine view to see their location and orientation. This machine has 3 tool racks, 1 horizontal and 1 vertical, and 1 additional turret. On the turret, the active station is shown, and when the tool is clicked, NCSimul displays it in its working position. This is how to configure a turret with the NCSimul tool magazine function. First, select tools coming from a prepared NCSimul tool library or from a tool management system such as NCSimul tool or TMS Solar. Clicking on this list allows for access to the graphical shape and tool assembly information. To load a tool on a station, switch into machine view, select a station, select the tool, and right-click on it. Tool 20 was loaded on station 20 and tool 21 onto station 21 respectively. To put several tools onto one station, use a multiple selection and then drag and drop to position them correctly. Each time a modification is made, the 3D window is updated. It's also possible to create a multiple tool station. First, put several tools onto a single station. In this example, there are 2 drills and 1 tap. Simply right-click on the station, select Merge, and they become a single station assembly. To customize the tool positioning within a station, first click on the tool in question and select the Set Position icon. Now, the translation and rotation modifications for Tool 21 are available. You can orient the tool on the station by angle, axis, or direction. It's also possible to modify a multiple tool. Access to each component to customize the positioning is still available, as shown here where the working side of Tool 29 is flipped. For mill-turn and Swiss machines, the NC simultool magazine function significantly reduces the tool preparation time. Complex multiple tools can be created in just a few clicks, and their subsequent positioning is extremely intuitive.
Now I would like to take the opportunity to highlight two improvements we did in the last version 2021.1. First, I would like to present the new function we put in this version. The new function is an analysis function to analyze what we call singularity point, and it's dedicated for 5-axis simultaneous toolpath to find the singularity point and also to analyze the performance of a 5-axis toolpath. Now, what is a singularity point? It's when you have a tool-axis vector and you are not able to calculate the rotary position. Any position can match, and we call that singularity point. And normally, a singularity point occurs when the tool axis is parallel to a rotary axis. And this singularity point occurs some very strange problem on the machining because after it's not the singularity point, but it's the point just after you can have a very big motion on rotary and you can damage your part because if you have big travel on a shorter tooltip way, it's similar that the tool run after the part and not cut correctly. You get very lot of vibration, and it's not it's occurs some cutting problem. It's why. And also there is there is two search in this function. You can first singularity point, and after this is the first parameter, and after the two other parameter is another research. You are looking for singularity which close to singularity which occur big rotation on rotary, and if you have a big rotation you can damage your part. And most of the time, yes, it's you have cutting trouble when you adjust after the singularity point. And during this computation, Antisimul does also what we call a setup performance analysis. That means Antisimul analyze the difference between the programming feed rate and the tooltip resulting feed rate. And here you can see the block, you can see the programming value, and we calculate what we call equivalent feed rate on the tooltip. And most of the time you use RTCP function to do 5-axis. You program one feed rate, but the machine is not able to respect this feed rate because you have some rotary axes are not very fast. Sometimes the part is very far from the pivot center, which occur long travel in XYZ. It's why automatically the machine slow down the axis, and the result is you don't cut with the programming feed rate. And it's why an Ansisimul recalculate this feed rate and in take in account the maximum possibility of each axis. And at the end, in the report, you have what we call the quality 5-axis. It's an indicator. That means during the toolpath number 3, number 4, and number 11, you respect your programming feed rate during 87%. And here you can see 50% for the last tool. That means you are not able to cut with your programming cutting feed rate. And as you don't cut with programming feed rate given by the tool builder, you can damage your tool, or you don't cut in good condition. It's why this tool is very useful to find to predict cutting program before going to the shop floor. Well, this function is very useful to solve your problem, because you can use this function before programming your complete program. You can just program the finishing toolpath in 5-axis, load the program in NC analyze the singularity, and the goal is to decrease the number of singularity points, because more you have trouble. And with the 5-axis performance analysis, you can also find the best plate or the best position of your part on the machine. Normally, you need to be very close to the pivot center. That means at the intersection of the two rotary axis. More the part is far from this center, more you have performance problem. And the orientation, sometimes it's better to put the part on another position to avoid to have singularity point. It's why you can use anti-simul very quickly in your programming process, just by simulate programming the 5-axis finishing toolpath, maybe in 5-axis, and simulate this toolpath to find the best place and best position to have the correct feed rate during 5-axis operation.
The new version of NC-Simul can calculate singularity points to analyze toolpaths that could potentially cause wide and unstable rotary movements in 5-axis, like a small tip movement with a high tilt variation. This function is available immediately after decoding, before even needing to run a simulation. When clicking on Singularity Point Analysis, it will open a ribbon where the tolerances are to be set. In these, define the limits of the singularity vectors. These values are saying that anytime a toolpath has a value between 0 and 0.001 degrees that results in a rotary motion of more than 60 degrees, throw up an alarm. Next, run analysis to receive a report for NC-Simul's decomposition of each tool sequence. There is a quality of 5-axis column, which is showing what percentage of the tool motion is respecting the proper programmed cutting conditions. And there are also columns displaying the number of singularity and turnaround errors as well, wherein the 60-degree axis motion limit was exceeded. Clicking on a field in the table jumps directly to the location in the G-code where the problem occurred. In the turnaround field, for instance, there is nearly a 90-degree rotation on a single block while machining in 5-axis, which makes it nearly impossible to achieve a good cutting condition in that area. There is a long travel on the machine for a very short tool tip travel. Opening the status window shows the program feed rate of 2,000 millimeters per minute and the actual feed rate achievable on that block not remaining constant and only reaching about 98 millimeters per minute. The machine limits the feed rate due to the rotary axis, since the tool tip is moving less than 1 millimeter in that time frame. All of this can be used to find the best possible setup point for the part on the machine table, limiting the distance to the pivot center of the axis, and finding the best orientation to decrease the number of singularity points. By doing this, the number of jerk moves will decrease, increasing the quality of machine surfaces, tool life will improve, and the final product will more consistently reflect the program tolerances.
The next improvement we did, it's an automatic intermediate stock management. It's the goal is to simulate only what it's needed. And the benefit of this function is to reduce the troubleshooting, because you restart always the simulation from the last intermediate stock update. To do that, there is a new icon in the simulation ribbon, and there is a new 3 icon here. You can activate this new function. You can delete the restock, and you can do a simulation, synchronized simulation. In this case, you use automatic mode, and the simul will start the simulation always at the good point. And you have also a new icon in the tree. You will see the program, and after you will see all tool sequence, and you have a green mark, and will show you if you have or not a restock for this tool sequence. And during loading a G-code, when you load a new version of your G-code file, and Simul compare it's a smart comparison, compare the existing one you have in your process, in your project, with the new. And after decoding the new, he compares the trajectory to be sure, and when there is something difference, he removes the restock automatically from this point. It's why after decoding, when you push simulation, anti-simul will start automatically and at the first tool sequence after the modification. And you can also unselect this button if you don't want restart from this point. If you would like to restart from the beginning, you have just to unselect this function, and you can redo a complete simulation. And it's possible also to remove manually some intermediate stock, and you can do a right click on a sequence, select the delete intermediate stock, and automatically NCSim will remove all restock from this point, and when you restart simulation, you restart from this point.
With NC-Simul's new intermediate stock management, running additional simulations after modifying toolpaths or G-code directly can perform up to 50% faster. Inside the simulation ribbon, there is a new group where it's possible to activate, delete, or synchronize intermediate stocks. When the simulation is started, the resulting stock will be calculated at each tool sequence, and once saved and available, will be shown with a green icon. During the first simulation, it is a complete computation for all sequences. If the simulation is reset and played again, nothing will happen because everything is still synchronized. Instead, by clicking throughout the program window, the material removed is shown up to a specific block. If a modification is necessary in the G-code, either repost it from the CAM system or simply modify it from the text file directly. When reloading, NC-Sim will then compare the modified file to the original one and identify where the parts began to differ. Any material removal in the simulation that occurred before that point is still held in memory as shown by the green icons in sequences 1 through 5. Now when playing the simulation, it will start at this point. This becomes extremely useful for reducing troubleshooting time as the programmer can immediately see the effects that the modification had on the machining process. By doing this for any collision or improperly machined location due to a fixture, tool, coordinate system, or beyond, it becomes even easier to quickly get a verified program out to the shop floor, ready to hit cycle start and run immediately.